Principles of electrostatic XY displays. An XY display is the visual interface between a generally complex electronic system and a human operator or observer. XY displays are designed for use as visual output devices in computer graphics systems, automatic test systems, medical systems, and electronic instruments such as spectrum analyzers, network analyzers, Fourier analyzers, and so on. Hewlett-Packard displays can easily be tailored to a wide range of applications, as many of the operating and input parameters are adjustable or switch selectable to fit a specific interface requirement. Refer to Hewlett-Packard Application Note 166 for more information about interface modifications. This program explains some of the terminology associated with XY display specifications and discusses the functional block diagram for a typical electrostatic XY display. Hewlett-Packard displays use an electrostatic deflection CRT to provide high-speed dot, vector, or raster displays in the X and Y axes, with intermediate intensity or gray shade capability in the Z-axis. To display a dot, voltage steps at the X and Y inputs position the beam to the required location, and a short duration intensifying pulse at the Z input illuminates the spot. The process is then repeated with different X and Y voltage levels for each new dot position. To display a vector, X and Y voltage steps first position the beam to the starting point. Then, the Z-axis input voltage turns on the beam for the required length of time as voltage ramps applied to the X and Y inputs move the beam across the CRT. The CRT is then blanked, and different X and Y inputs reposition the beam for the next vector. For raster generation, the X input is a series of ramps which sweep the beam horizontally, while a Y input ramp moves the beam down the face of the CRT. For some applications, the ramp signals to the X and Y inputs are reversed. The Z-axis input then intensifies the beam whenever information or video is to be displayed. A partial or mini raster positioned by X and Y voltage steps is often used for character generation. Now, let's discuss some of the terms used to specify XY displays. First is linearity. Linearity expresses the ability of a display to transfer specific X and Y input position voltages to specific beam positions on the CRT in a linear relationship. Linearity is measured along the horizontal and vertical center lines of the CRT and expressed as a percent of full-scale deflection. For example, a nonlinear display might position the halfway point of a long vector here instead of here. Linearity is often confused with geometric distortion, which would cause a straight line to be displayed like this instead of this. Closely related to linearity is linear writing speed. This is the fastest speed at which a visible beam can be deflected across the CRT and still meet linearity specifications. The beam can be deflected at speeds much higher than the specified linear writing speed, but with degraded linearity. Linear writing speed determines the maximum amount of data that can be displayed without flicker. Next is brightness. For a given CRT, trace brightness depends mainly on three variables: the type of phosphor, the writing speed, and the refresh rate. A change in any of these factors will affect the brightness of the trace. That is, brightness is directly proportional to refresh rate, but inversely proportional to writing speed. Refer to Hewlett-Packard Application Note 166 for a detailed description of how to calculate display brightness. The next term we will discuss is spot size. Spot size determines the resolution of a display. The smaller the spot size, the higher the resolution. Spot size is defined as the width between the 50% intensity points of a well-focused spot or line having a specified brightness level. When a photometer scans the spot or line, the resulting intensity graph looks like this. Spot width is then measured from here to here. Because the human eye sees this much of a spot, it cannot accurately discern where the 50% points are. If, however, several lines are merged, their intensity graphs begin to overlap. As these lines are merged closer and closer, the point where they can just be distinguished from each other with the eye is the 50% point on the algebraic sum of their intensity graphs. This is called the shrinking raster method of measuring spot size. A raster, having a known number of lines, is reduced in size until the lines can just be distinguished from each other. Then, the size of the raster is measured and divided by the total number of lines. The result is the average spot size of the display. Another CRT display term is diagonal settling time, sometimes called large step settling time. This is the time required for the beam to settle within a specified distance of a new position in response to voltage steps applied to the X and Y inputs. When any on-screen command is applied to the X and Y inputs, the beam will move to the required location and settle within specified limits in less than the specified time. Closely related to diagonal settling time is sequential point plotting time, or small step settling time. This is the time required for the beam to move and settle to within a specified distance of the final value when short-distance stepping commands are applied to the X and Y inputs. Small step settling time determines the time needed to write vector or dot matrix characters without smearing dots or bending the vectors. Repeatability is another display specification. This is an expression of how accurately a given set of X and Y input voltages will repeatedly reposition the beam to the same point on the CRT face after the beam has been deflected from that point with any other on-screen X and Y input voltages. Repeatability error is usually specified as a maximum % of full screen deflection. The last display term is orthogonality. This is actually an adjustment rather than a specification. This control allows separate rotation of the Y-axis to permit 90-degree alignment between the major axes. With these terms in mind, let's discuss the block diagram of a typical electrostatic display and the functional relationships of the major circuits. We will use the block diagram for a large screen display because it contains most of the circuits found in electrostatic displays. Other displays may differ in circuit content, but most are similar to the following discussion. We will begin with a look inside the CRT. Beam generation and shaping is accomplished with an electron gun which contains a cathode and a control grid and an electronic lens consisting of the first accelerator, a focus ring, and an astigmatism control element. Deflection is accomplished with X and Y axis deflection plates. The expansion mesh acts as a magnifying lens. The beam is further accelerated by the post-acceleration potential before it strikes the phosphor coating on the CRT face. In addition, small exterior coils are placed around the X and Y axis deflection plates to allow trace alignment and orthogonality adjustments. Refer to Hewlett-Packard Application Note 115 for further information on CRT operating principles. The CRT requires high operating potentials in order to produce an electron beam. This high voltage power supply provides a negative 4,500 volts to the cathode and a positive 24 kilovolts to the post-accelerator terminal, a total of 28.5 kilovolts beam accelerating potential. The X and Y channel amplifiers provide beam deflection voltages to the X-axis and Y-axis deflection plates and beam position information to the dynamic focus and astigmatism circuits. The Z-channel amplifier provides beam intensity control through the high voltage power supply to the CRT control grid. A Z-axis signal, proportional to beam current, is also applied to the dynamic focus amplifier to correct CRT focus for variations in drive levels. Deflection outputs from the X and Y channel amplifiers are combined with an on-off switch to form a logic signal to the phosphor protection circuit. The phosphor protection circuit operation is similar to a logic OR gate. If X-axis deflection is present, or Y-axis deflection, or if the phosphor protection switch is off, CRT beam current will not be limited. If the phosphor protection switch is on and no deflection occurs in both the X and Y channels, indicating a stationary beam, the phosphor protection circuit will limit the Z amplifier output to prevent CRT burns. The on-off switch located here allows the phosphor protection circuit to be disabled. However, in normal applications, this is not recommended. The dynamic focus and astigmatism circuits use X and Y deflection signals to keep the beam focused and shaped as it is moved across the face of the CRT. As the electron beam is deflected away from center screen, the distance it must travel before striking the phosphor increases. In other words, beam 1 doesn't have to travel as far as beam 2 to strike the phosphor. This causes a slight defocusing of the display. This problem can be minimized by varying the focus and astigmatism voltages as the beam is deflected. If we plot the change in focus grid voltage required to keep the spot in focus as the beam is deflected from center screen to either side, or from center screen to top or bottom, the curve will be parabolically shaped, with the least positive voltage at center screen. It's also symmetrical. That is, the change for a given movement to the left is the same as that required for the same movement to the right, or up, or down. The curve is shaped the same for both dynamic focus and astigmatism control. The dynamic focus circuit converts the linear deflection voltages from the X and Y amplifiers into parabolic voltages with nonlinear amplifiers. The outputs are summed and then combined with the front panel focus control level and the beam current signal from the Z-axis. The dynamic focus signal is amplified and applied through the high voltage power supply to the CRT focus grid. The astigmatism circuit applies a similar signal to the astigmatism cup to keep the beam rounded. The low voltage power supply provides regulated voltages of plus 15 volts, minus 15 volts, and plus 250 volts. In this program, we have defined an XY display. We have explained some terminology associated with XY displays. And we have discussed a functional block diagram for a typical electrostatic XY display. Application Notes 115 and 166 are available from Hewlett-Packard at no charge. Contact your nearest sales and service office for these and other application and service notes.
This presentation is directed towards the service technician responsible for maintenance of the Hewlett-Packard models 1310A and 1311A high-speed graphic displays. The 1310 and 1311A are large-screen electrostatic deflection displays. They're designed primarily for use as visual output devices in computer graphics systems, automatic test systems, medical systems, and similar applications. Subjects to be discussed include mechanical layout, signal flow to the block diagram level, unique specifications and adjustments, and a demonstration of CRT removal. Electrically, the 1310 and 1311 are identical, differing only in CRT size and front panel control locations. The 1310 has a 19-inch CRT with front panel controls across the bottom for focus, astigmatism, position X, position Y, power on indicator, and intensity. The 1311 has a 14-inch CRT with the same controls mounted vertically along the right side. By loosening two screws, removing the intensity knob, disconnecting the quick disconnect plug for the power on indicator, the plastic mask can be removed. This exposes other controls used less frequently: orthogonality, trace align, gain X, and gain Y. On the rear panel are the power on switch, line input and voltage selector, and X, Y, and Z axis signal input connectors. The bottom side of the instrument exposes the low voltage power supply, high voltage regulator, and high voltage rectifier. Notice that most board connections are made with edge connectors, permitting convenient board removal. Here's the CRT post-accelerator connector. Anytime this is disconnected, it should be discharged to ground immediately as a safety precaution. All other circuitry is located on the top side. Z-axis amplifier, Y-axis input, Y-axis output, X-axis input, X-axis output, and focus astigmatism board. An extender board is also provided. Now let's discuss signal flow. Here's a simplified block diagram showing the X and Y-axis input and output deflection amplifiers. The Z-axis amplifier, which provides intensity and blanking control for the CRT, a low voltage power supply, and a high voltage power supply. The low voltage power supply is a standard regulated supply configuration. The AC line voltage is stepped up, rectified, and applied to series regulating devices which maintain constant output levels regardless of line or load variations. The low voltage supply provides plus 15 volts, minus 15 volts, and plus 250 volts. The high voltage power supply provides the necessary voltages for the CRT. Plus 15 volts from the low voltage supply provides operating bias for an oscillator circuit, which drives a step-up transformer. The high voltage AC developed on the secondary winding is rectified, filtered, and applied to the CRT cathode and control grid. The high voltage AC is also applied to a voltage octupler, where it's rectified and multiplied by a factor of 8. The 24 kilovolt output is applied to the CRT post-accelerator. The output level of the secondary winding is monitored by an error detector. If the voltage varies from normal, the detector provides a correction signal to the oscillator to change the primary voltage, compensating for the variations. Now let's examine the high voltage supply in more detail. The quiescent grid-to-cathode bias is developed across R4, part of a DC restorer circuit. The 50 kHz AC output from the oscillator is transformer coupled through a current limiting resistor and coupling capacitor into the DC restorer. On 1/2 cycle, current flows through CR3 and R4. On the other half cycle, current flows through CR2. The voltage drop developed across R4 provides a negative voltage on the grid of the CRT. Looking at a more complete schematic, we find that the Z-axis amplifier is tied into the circuit through clamping diode CR4. The intensity limit pot is connected into the circuit through clamping diode CR5. During the positive excursion, the AC voltage at this junction will be clamped by CR5 to the DC level established by the intensity limit pot. And, during the negative excursion, the voltage is clamped by CR4 to the DC output level of the Z-axis amplifier. Therefore, the voltage drop across R4 will be a function of the difference in voltages between the intensity limit pot and the output of the Z-axis amplifier. For example, if the Z-axis amplifier output is at 60 volts and the intensity limit pot is set for 100 volts, then the voltage excursion at this junction will be 40 volts. Since the grid voltage is always referenced to the fixed cathode potential, the grid will accurately track the output of the Z-axis amplifier. The focus grid circuitry is similar. Next, let's discuss the X and Y axis deflection circuits. The inputs are fully differential. A triaxial cable is used, with the center conductor going to one side of the input, the shield going to the other side, and a grounded shield around both of these. Instruments are shipped in a single-ended configuration, but are easily changed to differential operation by changing this resistor value from 47 ohms to 10 k ohms. X and Y deflection factors can be varied by removing these jumpers and changing these resistor and capacitor values. Section 3 of the Operating and Service Manual provides complete instructions for these modifications. Input impedance can be switched between 10 k ohms and 50 ohms with this switch. Here's where the switches are located on the X and Y axis input amplifier boards. Incoming signals are coupled through impedance converters and amplifiers to a current controlling device, where signal gain is controlled. Because of the large physical size of the displays, cable length poses a major problem. For this reason, a DC-controlled electronic attenuator is used to vary signal gain. Let's look at the first stage of the deflection amplifiers without gain control. After passing through the impedance converter, the input signal is applied to the bases of U1, Q1 and U1, Q2. The signal current, I1, through the emitter resistance is the input to operational amplifier Q8, A and B. Here's the same circuit with the electronic attenuator added. Signal current I1 is now divided into two parts. One part flows through U2, Q3 and on into the operational amplifier. The remainder is diverted through U2, Q4 and then shunted out of the circuit. By varying the DC bias on U2, Q3 base with a front panel gain pot, we control how much current is coupled to the operational amplifier or is shunted out of the circuit. The operational amplifier output is applied to a differential amplifier and then to the CRT deflection plates. Deflection signals are also applied to other circuits for dynamic focus and astigmatism control. Another output, a logic signal, is sent to the phosphor protection circuit. We'll discuss these circuits later. The Z-axis circuitry controls the brilliance of the display. The rear panel Z-axis input signal and the front panel intensity control together vary the voltage on the CRT control grid. Input impedance is selectable here too, 10 k ohms or 50 ohms, with this switch on the Z-axis amplifier. Pads are also provided for adding an input attenuator. Incoming signals are coupled through a source follower to a double-ended current amplifier. This permits selection of either positive or negative signals for blanking control. Here's the switch on the Z-axis amplifier board. The current amplifier output is summed with the intensity pot current, amplified, and applied to the CRT control grid. With no external signal applied, the Z-axis is controlled entirely by the intensity pot setting. Another input to the Z-axis circuitry is from the phosphor protection circuit. This circuit monitors the outputs of the X and Y deflection amplifiers and operates similar to an OR gate. One of these two inputs must always be present to keep the phosphor protection circuit in an inactive state. If there's no deflection on either axis, indicating a stationary beam, the phosphor protection circuit will activate and limit the Z-axis output level to prevent CRT burns. An on-off switch, located here, allows the phosphor protection circuit to be disabled. However, in normal applications, this is not recommended. If trouble occurs, first check the low voltage power supply and then the high voltage power supply. Remember that the operation of the plus and minus 15 volt supplies and the high voltage power supply is dependent on the output level of the plus 250 volt supply. If the high voltage power supply output levels are incorrect, the CRT won't function properly. If trouble is suspected in either the X or Y deflection circuits, remember that the circuit boards are identical and can be interchanged for convenient troubleshooting. Now let's discuss unique adjustments. First, remove the static charge that's present on the CRT glass. With power on, hold the chassis with one hand and rub the other hand across the face and top of the CRT. This eliminates being surprised by a low current arc later. This charge can't hurt you, but it is unpleasant and might cause you to jerk while making an adjustment. Our first adjustment is Z-axis balance. Check to see that the phosphor protection switch is set to on. Now, with no X, Y, or Z-axis signals applied, adjust the intensity control until a dim spot is observed. Next, switch the Z-axis polarity switch between plus and minus while adjusting the Z balance pot for no change in spot intensity between positions. To adjust the dynamic focus and astigmatism circuitry, center the focus and astigmatism controls and position the spot to the center of the CRT. Next, connect a voltmeter to test point 1 on the focus astigmatism board. Adjust the focus balance adjust for an indication of plus 50 volts DC. If a dot pattern generator is available, connect it to the display and adjust it for a full screen raster of dots. If a dot pattern generator is not available, the dot can be manually positioned to each point of adjustment. First, locate the corner of the screen that has the best appearing spot. Leaving the focus and astigmatism control centered, adjust the focus limit adjust and astigmatism balance adjust for the best focused and roundest spot in that corner. Next, locate a spot halfway toward center screen along the X-axis and adjust X-axis astigmatism adjust number 1 and X-axis focus adjustment number 1 for the best spot at that location. Move the spot to the center of the screen along the X-axis and adjust X-axis astigmatism adjust number 2 and X-axis focus adjust number 2 for the best appearing spot. Now move the spot halfway toward center screen along the Y-axis and adjust Y-axis astig adjust number 1 and Y-axis focus adjust number 1 for best spot. Lastly, position the spot at center screen and adjust Y-axis astigmatism adjust number 2 and Y-axis focus adjust number 2 for best spot. This concludes our discussion on adjustments. All other adjustments are similar to those in standard oscilloscopes. Our final topic is CRT removal. We'll use a model 1311A for demonstration. However, the procedure is the same for both instruments. First, remove the CRT base socket and loosen the clamp. Next, disconnect the neck pins. Disconnect the post accelerator lead and immediately discharge it to ground. Remove the screws attaching the post accelerator connector to the deck. Remove the plastic mask and the 4 screws that attach the CRT to the front of the instrument. Now carefully slide the CRT out, being careful that the neck pins don't catch on the coils located inside of the shield. Since these large screen displays are used in a wide variety of custom systems, you'll probably see quite a few special versions. All of these use basically identical electronics, with only minor modifications. For instruments that do vary significantly from the standards, be sure to refer to the special documentation for the particular instrument. During the last few minutes, we've discussed the Hewlett-Packard models 1310A and 1311A, physical layout, general signal flow, some of the specifications and adjustments, and CRT removal.